Hi guys, Professor Burns here. We're going to look at section 3.1 where we're getting a little bit more into solving these linear systems using different analytical methods. So this first section we're just looking at linear systems, and I want to start off with just some general notation and information about how we would represent these. And by now I think we've talked a little bit about matrices and what we would do with those, and so we'll see how that kind of applies to solving these systems. So first of all, a linear system specifically, now we've talked about linear differential equations before, so a linear system is really similar. We're going to define it as dx dt is equal to ax plus by, so just like the equation of a line. And by the way, the coefficients for these are constants, so a and b would be constants. And then dy dt would be maybe dx plus, or let's do c rather, sorry. Cx plus dy. So that would be our linear system with constant coefficients. Now another way of writing this, and you'll see we kind of go back and forth, and it's really your preference which way you prefer, but we're going to start using matrices to write these as well. So first of all, what would we call the matrix for the coefficients? So the A, B, C, D, we would write this like this. So, and by the way, one more little piece of information. Again, I think I might have mentioned this previously, but if I haven't, on the notes, I have A as in bold, and a lot of times since you're writing it, you can't express something in bold, so what we'll do is we'll do like an A, a script A almost, with an arrow over it is another way of writing that. So if I write it in class with an arrow, that's what I'm talking about. But the coefficient matrix, we would just have a 2 by 2 matrix, A, B, C, D. Oops. The variable matrix would be would just have the two variables x and y. And again, I've got a bold y here, so I'm going to write like this. And that would just be x, y, like so. So the differential equation matrix with our two equations would look something like this. And I may write this, I know this notation gets crazy, but we've got d, and then I'm going to use a little, the arrow again, dt. And that's going to be equal to, so that's dx dt, dy dt. That would be the product of those two matrices I have above. And just a quick refresher about multiplying matrices. Remember, we talked about this a little bit in class, but I want you to just think about how this kind of relates to what we have up here. If you distribute this matrix, right, if you multiply these out, we would have ax plus by is equal to dx dt, and then in the bottom we would have cx plus dy is equal to dy dt. So what I want you to see is that this is a way of writing this system of equations using matrices with the coefficient matrix and the variable matrix there. Now, the next thing I want to talk about are equilibrium solutions. So just like we talked about earlier in this unit, equilibrium solutions, that would be where everything is equal to 0. So we're looking for where our system, both equations, are equal to 0. And just like always, we would just set the dx dt, so ax plus by equal to 0, and the dy dt, cx plus dy, again, equal to 0. And we would solve that system of equations to find our equilibrium solutions. Now, how do we express the general solution when we have a system like this? Well, one thing to consider is that we have this thing called the linearity principle, and I'm not sure if I put this in your notes or not, but this, let me write it here. This is based on the same principle we used way back when. It's kind of analogous to what we did when we were working with just a single differential equation, but it says if y of t, we know that, is a solution, then so is k times y of t. In other words, any multiple, constant multiple of that would also be a solution. Likewise, if y1 and y2 are particular solutions, then we know that y1 plus y2 would also be a solution. So another way of expressing the general solution, so for that bold y, I'm going to do capital Y with the arrow of t, would be equal to k1 times the first particular solution plus k2 times the second particular solution. And so when we're asked to write the general solution, this is a format that we're going to use. Okay, so let's actually apply some of these notations and get our feet wet with what these solutions are going to look like. So I've got a system of differential equations here. Notice that these are linear and they have constant coefficients. And part A says, write the component system in matrix form. And I'm not sure if I used that term yet, but this is also called the component system, the way it's written. So we're going to break this down, and what they want us to do is use the matrix notations that we talked about back up here, and that's all. So let's go ahead and break this down. I'm going to say then that dy dt, the vector form, is going to be equal to, so it's going to be the coefficient matrix basically times the variable matrix. So the coefficient matrix would be 2 and 3, and then notice there's no x for the second term, so that would be, or the second equation, that'd be 0, -4, and then of course the variables are just x and y. So this would be the matrix form of this component form of the system. So for the second part, they're giving us two particular solutions, and they just want us to verify those. So I'm going to use this matrix notation that they've given us. And for the first, the y1 that they gave us, notice that the derivative of this would be 2e to the 2t, and of course 0. So the idea is like, this is your x and this is your y. So if I write, let me go ahead, I'm going to write the matrix version here. I've got 2, 3, 0, -4, and I'm going to substitute in the x coordinate, the e to the 2t, and then the y coordinate, I'm going to substitute in 0. And the idea is that that should equal dy dt. In other words, that should equal the derivative of the entire expression. Well, all right, if we multiply this out, we would get, just double check here, we would get 2 times e to the 2t, and then plus 3 times 0. Does that, in fact, equal dx dt? That's the question. Well, dx dt, remember if this is x, dx dt would just be the derivative of e to the 2t. And you can see, yes, that does work. And I would check it for both of them, both the x and the y component. So if we do the same thing for the dy dt term, we're going to have 0 times e to the 2t plus -4 times 0. Does that, in fact, equal, what would dy dt be? Well, it would just be 0. So that would be good to go. Let's do the same thing with the other expression, the other solution that they gave us. So I'm going to write 2, 3, 0, -4. And if I substitute in -e to the -4t and 2e to the -4t and then multiply that out, let's see what that gives us. So that would give me, let's see, -2e to the -4t and then plus 6e to the -4t. And the question is, does that in fact equal dx dt for this expression? Well, little chain rule there, that would be a positive 4 e to the -4t. And you'll notice that, in fact, those are equal. So that is a solution. Check the other way. You're going to have 0 times e to the -4t, let's see, minus 8e to the -4t. And again, does that, in fact, equal dy dt for this part? That would be -8e to the -4t. So yes, we are good to go. Both of those do, in fact, give you particular solutions. So then it just says to put all this together and use that linearity principle to find a general solution. Let me clean this up a little bit here. So the general solution then, we know that the linearity principle tells us that our general solution in matrix form or vector form is going to be equal to K1 times the first particular solution, so that was e to the 2t 0, plus K2 times the second particular solution, so that was -e to the -4t, and then 2e to the negative 4t, and that is going to be my general solution. Just like previously we had C1 and C2, it's the same idea. That's what those are. We don't have an initial condition to solve for K1 and K2. If you were to write this in component form, if they said to write your answer in component form, just for good measure, let's do that real quick. We would say that my system is x of t would be equal to K1 times e to the 2t, and then minus K2 times e to the negative 4t, and then the y component would be written as 0, of course, for that first term, and then 2K2 e to the negative 4t. These are equivalent answers, and unless they specify a certain format, either of these would be acceptable for your answer for the general solution. So then the last example here, they want us to find the particular solution with this given initial condition. So let's just be clear on what this tells us. This tells us that, remember, this is a function. So time is like the independent variable, but x and y both depend on time, basically. So we would say that when t equals 0, we know that our vector components are 2 and negative 3. So the x component would be 2 and the y component would be negative 3. So if we put this, let me kind of leave the screen here so we can see it. If we put this in for our components, I'm going to use the matrix form just to get a little practice with that. We know that they're saying that on the left side, we're going to have 2, negative 3, and that should equal K1 times e to the, now remember, this is when t is 0, that's what that tells us, e to the 0 power, and then 0, plus K2 times negative e to the 0 power and 2e to the 0 power. And then we're going to simplify this, and we're going to have a system of equations we can use to solve for K1 and K2. So I've got 2 equals, so go across, take care of the x component first. E to the 0, of course, is 1, so that's going to be K1. Same thing here, plus K2, and oh, sorry, that's negative. It's going to be a negative 1. Let me fix that. So that would be, that would be minus K2, just because of that negative sign, because that would be negative 1. And then the other, the y component, you're going to have negative 3 is equal to 0 times K1, and then 2 times e to the 0, of course, is 1, so 2 times K sub 2. So you're going to solve this system of equations, and we can solve right away and see that K2 is equal to negative 3/2. So then just go back and substitute that into the original expression, and we're going to say that 2, of course, is equal to K1 minus negative 3/2. So K1 is equal to 1/2. So then what does my particular solution look like? So I'm going to call this y, and I'm going to call it y sub p. The particular solution is equal to 1/2 times e to the 2t 0 matrix, and then minus 3/2 times negative e to the negative 4t, and then 2e to the negative 4t. And that's going to be our particular solution for the given initial condition. All right, I think that's it. We're going to do a little bit of practice with this, and I'll see you in class.